Welcome to this explainer. Have you ever felt like calculus is just a bunch of disconnected algebraic rules? Well, today we're fixing that. We are going to dive right into calculus by grounding abstract theorems in everyday physical reality to make them perfectly clear. We're going to bridge that gap between what you experience out in the real world and the exact mathematics that describe it.
Okay, let's look at our roadmap for today. We've got 1. Average versus instantaneous change. 2. Rolle's theorem explained. 3. The mean value theorem. 4. Conquering indeterminate forms. And finally, 5. The shape of curves. Let's see how these 5 concepts are really just formal expressions of common sense logic.
Section 1. Average versus instantaneous change.
We're going to start with a highly relatable, real-world physical scenario to anchor your understanding before any heavy algebra begins. Math is rarely just numbers on a page. It's the invisible clockwork behind moving objects. Imagine you're driving. Over a specific interval, your average speed is 44 feet per second. You took exactly 8 seconds to travel 352 feet. But how does math actually prove you hit a very specific, instantaneous speed during that trip? Think about it. You didn't just teleport at an average speed. You had to accelerate, maybe coast a bit, and speed up again.
Well, the mean value theorem proves that at some exact, instantaneous moment during that 8-second acceleration, your speedometer absolutely had to read exactly 30 miles per hour, which is 44 feet per second. If your average speed is 30 miles per hour, there's a rock-solid mathematical guarantee that you traveled exactly that fast for at least one infinitesimally small fraction of a second. No way around it.
Section 2, Rolle's theorem explained.
Let's see how our speeding car analogy builds into this next concept, which is basically the strict mathematical translation of the old saying, what goes up must come down. What's really fascinating here is translating pure algebra into geometry. We've got 3 strict conditions. First, the function must be continuous on a closed interval. In plain English, you can draw the entire line from point A to point B without lifting your pen once. Second, it has to be differentiable on the open interval, meaning absolutely no sharp corners or jagged edges. It has to be perfectly smooth. And third, your starting height must perfectly equal your ending height.
So, if you follow those 3 geometric rules, your start and end points are totally level, you didn't lift your pen, and there are 0 sharp corners, the math dictates that there has to be at least one flat peak. You literally have to change direction at least once to get back to where you started. And at that exact turning point, the tangent slope is a perfectly flat 0. That is Rolle's theorem in a nutshell.
Moving right along to Section 3, the mean value theorem.
This reveals how we can take Rolle's theorem, tilt it, and unlock the broader, much more powerful Lagrange's mean value theorem. The true power lies in comparing them side by side. Rolle's theorem requires the endpoints to be perfectly level. But Lagrange's? That's the general rule where the endpoints can be at completely different heights. If you draw a secant line connecting point A and point B, the theorem guarantees that there is at least one point in between where the smooth curve's tangent line is mathematically parallel to that secant line.
Mapping our speeding car analogy into rigorous math makes the connection perfectly clear. The average change over an interval, that's the slope of the secant line, equals the exact instantaneous change, or the slope of the tangent line, at some point C. That first formula, f of b minus f of a divided by b minus a, is your average trip speed. The other formula, the derivative, f prime of c, well, that's the exact moment your speedometer needle perfectly matched the average.
Section 4. Conquering indeterminate forms.
Let's dive into where derivatives become the undisputed heroes of solving seemingly impossible limits. Sometimes, when you try to find a limit by just plugging in numbers, you hit an absolute brick wall. You get 0 divided by 0 or infinity divided by infinity. Because these indeterminate forms don't reveal the true answer, we can't just plug in the numbers and walk away. We need a special mathematical tool to smash through that 0 over 0 wall and find out what the function is actually doing.
Enter L'Hopital's rule. This is a brilliant technique that lets us completely bypass that dead end. When a limit gives you 0 over 0, you simply take the derivative of the numerator and the derivative of the denominator completely independently. You don't use the quotient rule here. You just look at the top and bottom as their own separate entities, find the derivatives, and try taking the limit again.
But hey, remember that math is incredibly strict about its rules. L'Hopital's rule only works if you actually have an indeterminate form. Now, you might have to apply it multiple times in a row if the result is still 0 over 0. But and this is absolutely crucial, you must stop differentiating the second it's no longer an indeterminate form. If you get careless and keep applying the rule after the 0 over 0 form is gone, you are going to get a completely wrong answer.
Section 5. The shape of curves.
Let's move to our final concept and see how everything we've talked about builds into curve sketching, mapping the invisible shape of any mathematical function. This perfectly highlights the division of labor in calculus. Think of the first derivative like a compass for direction. It tells you exactly where the graph is rising and falling, which pinpoints your local maximums and minimums. The second derivative, on the other hand, measures the actual bending of the curve itself. It tells you if it's curving upwards, like a bowl, or downwards, like an umbrella.
And that brings us to the point of inflection. This is the exact defining moment a curve stops bending one way and starts bending the exact opposite way. It stops bending like a smile and starts bending like a frown, or vice versa. It's the precise spot where the second derivative hits 0 and actually changes its sign. So, by putting it all together and following a precise 6-step procedure, you can accurately graph incredibly complex functions without ever touching a calculator. You figure out the domain, map the slopes using the first derivative, chart the bending with the second derivative, find exactly where things change direction, and then just connect the dots based on the calculus. It's like putting together a giant puzzle where math gives you all the pieces.
Now, before we wrap up this explainer, we have to ask a really important question. What happens to our theorems if the function we're looking at suddenly breaks the continuous, smooth rules we established earlier? What if the function jumps abruptly, like a step function, or has sharp, jagged corners, like an absolute value graph?
Well, all of those mathematical guarantees just vanish. If a function isn't continuous or differentiable, meaning there's a sudden gap in the drawing or a sharp, sudden point, the magic of the mean value theorem and Rolle's theorem instantly fails. You can no longer guarantee a parallel tangent line or a flat peak. This proves just how vital those geometric conditions truly are. The math absolutely relies on the universe being smooth and continuous to make these specific guarantees.
I really hope this explainer has sparked your curiosity. We've seen how average trips conceal instantaneous speeds, how impossible limits can actually be conquered, and how equations secretly hold the literal shapes of curves hidden right there inside their derivatives. It kind of leaves you wondering, doesn't it? If calculus provides the rigorous framework that proves exactly how fast a car was speeding and maps the invisible shape of curves, just how many other everyday phenomena are secretly governed by these elegant mathematical truths? Thanks for joining me, and keep exploring.